Today what I'll be talking about is work from my PhD that we did looking at hidden Markov movement modeling, particularly with irregular data. And it's work that I did with Professor Paul Fatty, who I can see there, and Professor Norman Owen-Smith. So, hidden Markov models have become very popular for the analysis of animal tracking data, both in a marine and a terrestrial setting. Typically, the measures that are used as input for the model are the step lengths, which is basically the straight line displacement between successive GPS location points. And then the turning angle gives you the direction or the heading in which the animal is moving. And these are calculated from successive GPS locations that are obtained at predetermined intervals. Once you've fitted the hidden Markov model, the output includes the state-dependent distribution parameters. So that is basically fitting a particular statistical distribution to the data. Then the transition probability matrix, basically giving you an idea of the probability of shifting from one state to another. The stationary distribution, and from that we can then predict what's known as the latent states, the hidden states, and we actually interpret those states as being the behavioral state of the animal during the period of observation. So essentially what we're doing is taking these metrics obtained from the GPS locations, fitting a model, then using the parameters and the predicted state sequence to then make statements about the biology of the animal. There have been a number of advances recently in terms of animal tracking technology using GPS collars. And a lot of that has been in terms of actually the battery life. So now we are able to obtain many more observations over a short period of time, or very large data sets over longer periods of time. So to give you an idea, with some of the data that I've worked with recently, it was actually collected for a lion at 5-minute intervals, so very, very short time period, getting a whole lot of data. And others where collars have been recording at about every hour. The data sets span about 2 to 3 years worth of locations. One of the massive advantages of doing this is that it means that there is no human interference. Typically, if you want to observe an animal and see what it's doing, if you're actually out in the field, the presence of the human can actually interfere with the animal. Also, depending on what is being tracked, it can also be a danger to the human. So when we're looking at animal tracking research, our challenge is to link the statistical properties of the movement patterns to the behavioral characteristics of the animal. And typically what we are doing from the statistical side is fitting these models, obtaining information and patterns that then are interpreted by the ecologists and used further in their ecological research. The majority of GPS tracking has been done in the northern hemisphere, with very few findings published on African herbivores or predators. A little bit more work is coming out on African movement, but very little in comparison to what has been done in the north. So with this particular work that we did, an assumption of the model is that the input observations are equally spaced in time. So in other words, the collar would record a location every hour consistently. However, missing data are a common feature of remotely sensed movement data. So ideally, we'd like to have these very regularly spaced locations. In fact, that often is not the case. So there are a couple of reasons for why there can be missing data. One is that you actually just were unable to connect to sufficient satellites to obtain a location at a particular time. So that would be a failed connection. Often thick cloud cover, if the animal's in dense bush, those can lead to a lack of connection. There can also be, for certain species, the collars are actually set to record at irregular time intervals. And the reason for doing that is to try and get more fixes or locations when the animal is typically highly active. And by doing that, you can then extend the battery life of the collar. So, for instance, with predators, which is the data that we'll be using in this particular study, the collars were set to record regularly during the night when the animal was active, and not much during the day when less activity was expected. Another one that I worked on recently was actually for a brown hyena, where during the day they typically lie up in burrows underground. So in that case, trying to obtain locations during the day would mostly not work anyway, because it would be impossible for the satellite to actually connect a number of times. So often this irregular observation setup is chosen to extend the battery life of the collar. And when you have these irregular locations, if we want to then make them regular, you end up losing a lot of data. So if you're, say you're recording at 1 hour intervals during the day, during the night, and 4 hour intervals during the day, to make that a regular sequence, you would have to subsample the nighttime location to every 4 hours to end up getting that regular time interval between successive locations. So obviously this is not ideal. Collecting this data is costly, so we don't want to end up throwing it away. And there are a couple of options. The one we've used, and I will also come back to it at the end of this talk, is to actually calculate a rate over time. So for each gap or time period between locations, calculate the displacement distance, and then actually divide it by the number of hours that was between these 2 points. So that's the one way of doing it. Some studies have used interpolation, which personally I'm not a particular fan of. To me, there's enough error and uncertainty in what the animal is doing anyway to interpolate just adds more into that. So what our objective was for this particular area of the research was to find a method where you can combine the movement data from various timescales to be analyzed using the hidden Markov model framework, which requires these regular locations. So to give you a bit of the mathematics behind the hidden Markov model, for a stationary HMM, your likelihood function is defined as that equation that you can see on the screen, hopefully, where delta is the initial distribution. Then you have gamma, which is your transition probability matrix. And then you have a diagonal matrix of state-dependent probability functions. And in terms of fitting the model, you calculate your likelihood and then go and optimize it to find your maximum likelihood and then use those parameters as your maximum likelihood estimates. So what we decided was to actually modify that likelihood function. So what we did was essentially your transition probability matrix at each step is your probability of shifting from one state to another. And so what we did was to modify the likelihood where we were actually raising that transition probability matrix to a power, and that power was the number of time steps between particular observations. So if there was only say a 1 hour time step, you would just have your transition matrix by itself. If you had a 2 hour gap, you would then actually multiply that matrix by itself once. So you'd raise it, it would be essentially gamma squared that you would be using. And the interesting thing is that as your number of time steps between the observations increases, your transition probability matrix gets multiplied by itself an increasing number of times. So if you have 5 hours between successive locations, you would take that transition matrix and multiply it by itself 5 And as that number increases, so as your missed time steps essentially increases, that product ends up being a matrix with identical rows equal to the stationary distribution of the Markov chain with transition probability matrix gamma. So what's quite interesting is as you have more and more steps between them, you end up actually just having a single set of probabilities of being associated with each state, which in a way does make sense from the biological side, is that if you're used to spending, say, 50% of your time in a rested state, once you've had a large number of gaps between these successive locations, you're going to have less information. You're going to just have your sort of long-term average, essentially, is what this ends up being. So from a biological point of view, I think our interpretation of this modified likelihood model is still reasonable for what we are trying to do. And actually, in this case, when you have a large number of the time steps missing, the model that you end up fitting is actually an independent mixture model. And interestingly, the hidden Markov model is often known as a dependent mixture model. And when we actually set out working on my PhD research, we actually started using just an independent mixture model to actually model it. So in this case, where you've got a lot of missing locations and these irregular time steps, when you've got a large number of missing points, you end up actually fitting an independent mixture model. So the data for this particular study was collected from in the Kruger National Park up in the northeastern corner of South Africa. And hopefully what you can see now on the right-hand side, the orange dots are the locations of this particular lioness. It's for those of you who know the Kruger National Park, where you can see that horseshoe shape with the bulk of the locations, that is around Crocodile Bridge Rest Camp. And the greyish shading is the Kruger National Park, and then the white below is the area outside the park, and that boundary is actually the Crocodile River. So you can see that this particular lioness hung around in the same sort of area for a lot of the time. She also went on one particular journey where she actually moved along the river edge quite a lot. So the data for this particular study was set up during the night to record at 1 or 2 hour time intervals, and during the day to only record at 4 hour intervals. So to extend the battery life during the daytime, where lions are expected to be less active. In total, we ended up with 5,824 observations for this particular lioness. And as I said, lions are meant to be quite lazy during the day and spend a lot of time sleeping, or in this case, yawning and trying to go to sleep. And what was actually quite interesting with this particular Crocodile Bridge lioness, she was actually reasonably active during the day. And one of her longest movements was about a 3.5 kilometer journey that she made at about 2 o'clock in the afternoon. I think it was between 2 and 4 o'clock in the afternoon. So she is actually quite an active lion. We've had a look at some data for a lioness near Orpen, slightly further north, where that particular lioness seemed to do nothing during the day. She seemed to lie down and was very inactive during the day. So this one was actually reasonably active. So in terms of the actual model fitting, we tried fitting 2, 3, and 4 state models, and we used the log normal distribution as our state dependent distribution. Just as an aside, with hidden Markov modeling, typically some people use the displacement distance only. Some use the displacement and turning angle as the model inputs. And for this particular animal and quite a few others, we've actually fitted models using the displacement only, or both, and we've actually found that the output is not that affected by the inclusion of the turning angle. So for this particular study, we used just the displacement between successive locations. Our model selection was done using the Akaike information criterion, and the state allocation, once you've fitted the model, so you fit the model, you get your state-dependent distribution parameters, your transition probability matrix, your stationary distribution if you're fitting a stationary model, and then in order to get predicted state sequence, use the Viterbi algorithm. So basically it's taking your input distances, so your distances between successive locations, using that to fit the model and then predict this underlying or hidden state using the Viterbi algorithm. And for this particular lioness, we found that a 4-state model was selected as the best model, and that said, the AIC is just going to find which is the best model of the ones that you've fitted. It's not telling you that it most certainly is the correct model, but of the ones we fitted, 4-state performed as the best. So when we use this irregular input model, one of the main challenges is and was to actually interpret what these latent states meant. So what we first had a look was the expected displacement. So that is actually the expected value for that particular distribution fitted to state 1 or state 2, state 3, state 4. So it's the expected displacement is the expected value for the log normal distribution fitted to state 1. And the units there are kilometers. So in state 1, very short movements. State 2, about 160 meters. State 3, 600 meters. And state 4 at about 1.45 kilometers. So as you can see, the different states are picking up quite different movements that are being allocated to it. We also had a look at the average movement rate. So of the observations that were allocated to state 1, what was the average distance moved? And as you can see, they're slightly shorter than what the expected value from the distribution function is. But again, state 4, the more active state, state 3, a sort of intermediate distance, and state 1 and state 2, much shorter displacements. Then to try and understand what the model was actually finding, we had a look at, this is a bar plot of the frequency of the particular states by the hour of the day. So on the x-axis, you can see the hour of the day. And this sort of pattern is, and we'll have a look at what a model fitted slightly differently, but hopefully you can see that the red state, which is state 2, very dominant during the day. State 2, which we said was quite short movements, so very much the animal resting, not a lot of activity at this point. The other states, the black, green, and the blue, vary during the day. And what the interesting part with this, it wasn't the typical pattern that we would have expected for a lion. The point was that we were able to fit the hidden Markov model using this irregular data. How we go and interpret these states, that still needs some work and a decision about what are these states actually picking up, because presumably it is picking up something slightly different to what we normally get with a regular state hidden Markov model, or regular time step hidden Markov model. So as a comparison, what we did was used exactly the same data and then calculated the movement rate. So how far it had moved divided by the time gap between the locations. And if we plotted the exact same plot using that, this was just a 3-state model that we decided captured the behavior of this animal quite nicely. And the reason why we used the three-state model for this one was a state validation, which I'll explain just now. So in this plot, you can see the black state is definitely resting, particularly during the day. Late afternoon spends more of the time resting. The green state there is relocating, and you can see there quite a lot of relocation even during the day, less so late afternoon, and then picking up around 7 p.m. in the evening, somewhat more active at night. And this sort of pattern was what we obtained from the movement rate. Somewhat more interpretable in terms of what we'd expect the lion to be doing during those times of day. But the main thing, if we just go back and have a look at the irregular time plot, we certainly are there picking up the resting during the day. What the interpretation of those other states is does need some work. So the important thing here, and we'll touch on this again at the end with the conclusions, is statistically we were able to fit the model. So we were able to take the hidden Markov model that requires the regular time steps. We were able to modify the likelihood function. Statistically, we were able to fit the model. We now need some work, excuse me, in terms of the actual interpretation of these states. So the reason why we had a look at this movement rate model was for a period of time, they actually went out in Kruger and actually tracked this particular lioness. The pride was observed during various periods. The behavior was noted and kills were recorded. And this is quite unusual for hidden Markov models, or actually for any animal movement modeling, where we actually can uncover what the true state was. Normally collars are deployed, the animals move off, and we have very little idea of what they are actually doing during the time of observation. So with this particular pride, they went out on foot, mostly at night, and actually followed the pride. They tried to keep an eye on them to see what they were doing. Sometimes they would record what they were doing just based on noise and spoor, etc. But they tried to keep quite close to them throughout the night. So this is quite an unusual data set for us, in that it gives us a bit of an opportunity to try and uncover what the true state is. And when it comes to hidden Markov models applied to animal movement data, this is very seldom done. There was one study using the movements of wolves in Canada. They actually flew over the area that the wolves were moving in and tried to identify kill sites using sort of blood stains, etc., on the snow that they were able to pick up. Otherwise, very little work has been done to actually try and validate the state predictions that we make. So if we have a look, hopefully you can see a table here where we have the date and the times. The activity was what the researchers on the ground in Kruger actually recorded. So whether it was walking, resting, mating, and then what you can see is you've got the HMM movement rate model. And the first problem we had with this was that the timing of the GPS locations and the time scale of the actual observations in the field were very different. So now we were trying to validate states at different time scales. But if you have a look there from sort of 6:30, the pride was recorded as walking, at 7:30 as resting, at 8 o'clock mating, and at 8:30 walking again. And throughout that time, from 6:15 to 11:15 that night, the model predicted local movement. Then from 9 o'clock until 3:30 in the following morning, the pride was observed, or this particular lioness, to be mating and resting. And if we have a look at the model predictions, we had resting from 11:15 till 1:15, and then local movement. from 4 until 6:30 in the morning resting, which we also predicted, and then 7 o'clock walking, and the state prediction from the model was movement. So although it's not an ideal validation based on the timescales being very different, at least our state predictions are reasonable. Walking, resting, mating, walking, we predicted as local movement, which an animal that is sort of doing a combination of those particular activities, the prediction of local movement is not a bad one. In the same way, the mating and the resting, we had a mixture of resting and local movement. And then resting early in the morning, walking being movement. So it seems like the model is doing reasonably well. And of course, in terms of the actual state predictions and validations, we'd need to do far better in terms of matching up the time scale, etc. But at least this was something as a bit of a first stab at doing it. So with this particular data set, the main two things that we wanted to look at was, were we able to fit a model statistically using the irregular data, which we were. We were able to fit the model in terms of the actual predictions of or interpretations of the states. We need to do a bit of work on that. And then we were actually able to take the movement rate model and try and validate our states, which the results are encouraging. They're not perfect. But based on the timescales and the differences, and animals do throughout even an hour, if that was our tracking period, the animal is going to engage in a different combination of activities anyway. So in terms of the conclusions from this particular part of the research, when it comes to these irregular time step models, more in-depth interpretation of the behavioral states would be needed. And particularly in terms of the biology of the lion. The results that we've got are encouraging, but it certainly does need a bit of work in terms of the interpretation. The important point for us really was that the irregular data input allowed all of the data points to be used. So instead of throwing away a whole lot of the regular hourly observations at night and just sticking to a 4-hour model that could use day and night observation, we were now able to use all of the data. And from the statistical side, hidden Markov models are a very flexible technique for the modeling of these animal movement tracks. So in this particular one, we modified the likelihood function in terms of the input data. You can also, with hidden Markov models, quite easily include covariates into the models. So they have become increasingly popular as a technique for modeling the movement of animal tracks. And particularly in the recent sort of past year or so, there now even are packages specifically designed to fit hidden Markov models to animal movement tracks. And with what we did, we fitted the distributions via a Markov process where there are a limited number of missing time steps. And as we said, if the number of time steps increases substantially, you just end up fitting an independent mixture model anyway. So in terms of acknowledgements, my PhD supervisors, Prof. Fatty and Prof. Owen Smith, I'd just like to acknowledge them for all the hard work that they put in throughout the study. South African National Parks also provided the lion data, and experts there, Sam Ferreira, Paul Funston and Benny Maruping, played a big role in working through the lion data and what we could do, and also the National Research Foundation for a grant that I've got. So from my side, that's just to say thank you.